Lesson. Today's lesson is another calculus lesson. Isn't that so fun? Yesterday's lesson was calculus. Today's calculus. You're going to know so much calculus before you get to calculus. It's going to be like a breeze. You know, like, oh yeah, I know all that. What we're going to be doing today is we're going to be using the derivative. Yesterday we worked with the difference quotient. If you recall, that's this portion right here, and I explained that if you put the limit statement on front, you would be finding the derivative. All right, that's what this is. This is actually it's called the definition of the derivative. So this is the classic way to find derivatives, using the definition of the derivative. Very classic. As you work with this, though, you will find that for some types of functions, it is quite time-consuming to use this for everything. You can use this for everything. You can find the definition you can find a derivative of anything with this limit statement. But because it takes so long, mathematicians have come up with rules, or basically rules to find derivatives. There's a rule for each kind of function. Like we have a rule for polynomials. It's called the power rule. We're going to learn that today. That's the most basic derivative rule, is the power rule. There are other rules, like for fractions called the quotient rule, for products called the product rule, chain rule. There's lots of fantastic rules. One of the things I love about math is if you know the rules, you can do anything. So you just have to know the rule and memorize it. You can do anything. So we're going to learn the power rule today. We're not going to be finding the derivative today with the definition of the derivative. We're going to be learning the power rule. We'll just work with polynomials today. And I'm going to introduce you to some pretty important calculus topics today. So let's start with these theorems. This is what's going to help describe what the power rule is. So let's look at this first theorem. It basically says if f of x is a constant, in other words, say it's 2, if it's 2, then the derivative of that is 0. So what this is saying is that the derivative of every constant is 0. So the derivative of a million is 0. The derivative of -2 is 0. All constants, the derivative is 0. So that's what this first theorem is telling us. The second theorem is actually the power rule. That is the makeup of the power rule. So let's talk about how it works. It works with polynomials. This is a rule for polynomials. There are rules for all different kinds of functions. We are just dealing with the most basic rule, which is a polynomial. This says if we have f of x equals x to the n, x to some power, x to the n power, then the rule, what we do is we take this exponent number, that n, we pull it down in front of the x, and then we subtract 1 from that number. Okay, that's how that power rule works. So for example, if I had, say, x to the 7th, okay, and I wanted to take the derivative of x to the 7th, and I'm following this rule, I would bring the 7 down front, and then I would subtract 1 from 7 and get 6. So the derivative of x to the 7th is 7x to the 6th, using the power rule. Okay? That's how that works. So, are we okay with that? Okay, that's just the power, that's the power rule. So, Theorem 3 basically tells us what to do if there's a constant. What if there's a number in front of, like a coefficient, in front of the x that we're going to take the power of? What do we do? That's what this theorem tells us. If c is in front, we're going to do the process the same way. We're going to take the n, we're going to take it down front. It's going to be multiplied by the c, and we're still going to subtract 1. So for example, what if we were going to take the derivative of 3x to the 4th? What would we do? So we would take the 4, and we bring it down front. 4 times 3x to the 3rd, right, because I'm still subtracting 1 from the 4. So we clean that up and we get 12x cubed. So that's what Theorem 3 is telling us, is if we have a number already in front of the x, it just serves as a multiplier. That's all. Whatever number we bring down front, that's going to be the exponent number, we just multiply that. So I'm going to pause there for a second. That's a lot to take in. Are we okay with that procedure, that power rule? Okay. The last theorem tells us that if we have a combination, we're adding two different functions together, we are allowed to take the derivative of them separately. That's just a rule that allows us, like if you have a polynomial that has 5 terms, you would take the derivative of each term, one by one. This rule would allow you to take the derivative of each term one by one. Okay, that's all this is saying, is that you're allowed to do that. Okay, so those are the rules that we're going to be looking at today. So what do we use the derivative for? That's really the focus of this lesson. What are we going to use the derivative for? It's actually very important. You may know, or you may have heard before, that the value of the derivative at a particular x coordinate is the value of the tangent line at that location. I'm going to say it again. The value of the derivative, let's say we find the value of the derivative at x equals 3. That is going to be the slope of the tangent line at x equals 3. Okay, that's one use. There's many uses for the derivative, but that's the use that we're going to be looking at today, is how the derivative is related to its original function. We'll call it the position function. How is it related to the position function? So thinking about that, let's think about, we're thinking about little tangent lines, okay? And this graph right here, the original position graph, is the one that's blue. Okay, that's all three pieces are the same function. That's like we would call it f of x. So this red line is drawn here. That's a tangent line. We recall from geometry what tangent lines are, right? It's just it's tangent at a point, has a point of tangency. So this red line is a tangent line. What is the slope of this red line? Is 0, right? It's a horizontal line. Slope is 0. So what that means is at this x value, say -5, the value of the derivative at x equals -5 is 0, because that's the slope of that tangent line. Okay? What about, let's draw one here. Let's draw a tangent line right here. Let's talk about it. So let's say I have a tangent line right here. Okay? So this tangent line, I don't know, looks to be maybe a slope of 1. Something like that. 1 or 2, somewhere in there. So what that means is, again, at whatever that value is, I don't know, a little bit less than 1, at that x value, a little bit less than 1, the value of the derivative would be 1. Okay, are we getting the connection there? All right, so now let's look at what that means. Think about this section right here. If I drew tangent lines, they would be like that, right? What are the signs of the slopes of those tangent lines? All these little tangent lines, that's a negative slope, right? Look what the function is doing. See, the function is decreasing. See how it's decreasing there with those negative slopes? What about these slopes over here? Those are positive slopes, and what's the function doing? It is increasing. Okay, see how the derivative tells us the behavior of the position function. Okay, so let's just look here. What about these tangent lines? What's the sign of their slope? Positive, so we're increasing, and positive, increasing. So are we kind of getting the hang of it? So over here, the signs of these slopes would be positive, it's increasing, negative, decreasing. Okay? If my derivative is 0, some special things happen. Notice what's happening here at the derivative value of 0. I have a relative minimum. I have a minimum value here. Look what's happening over here, right here, when that derivative is 0. I have a relative maximum value. And other weird things happen. It doesn't have to be a relative min or max. It could actually, there's a tangent line right here. It could be a point of inflection. It doesn't have to be a relative min or max, or it could be just something weird. Okay, so when the first derivative is 0, that's significant for us and tells us information. Okay, so I want to pause here for just a second because I know that's a lot to absorb. Questions so far? Okay, let's look at these generalizations then. They really go off of this, what I'm talking about. So if the first derivative is positive on an interval, then the graph of f of x is rising as x increases. It increases. So if the first derivative is positive, we are increasing. Okay? If the first derivative is negative on an interval, then the graph is falling, so it's decreasing. And if the first derivative is 0, then the graph has a horizontal tangent at x equals c, which means they could have a local max, a local minimum, or a point of inflection. Okay, so those are conceptual things. How are we with the concepts? Okay, so how are we going to use this? So we're going to use it to do a couple of different things. And we're just working with polynomials, okay? That we do this in calculus with all different kinds of functions, okay? We are just doing just polynomials, the easiest functions possible. So here are the steps that we would take to find increase, decrease, and local extrema. That's what we're going to be doing today, is doing these things, finding intervals of increase, decrease, and local extrema. What do we do? The first thing we do is find the derivative. That's the very first thing that we do. The second thing that we do is solve the derivative. In other words, set it equal to 0. Okay? We want to set the derivative equal to 0. The third thing that we would do would be to create a sign chart. Okay, so we have done sign charts before, right? We've done actually fairly recently. We know how to do sign charts. So that's what we would do. We would do a sign chart. And then the positive sections of the sign chart are where the function is increasing. The negative sections are where the function is decreasing. And then we would determine local extrema from there. So I'm just going to kind of write an example up here. Let's see. I'm going to write a sign chart. I'm just going to make one up. Okay, let's say this is our sign chart. We had a sign chart and it, let's say it looked like this. And it went like that. Let's just say it did that. Okay? So let's talk about what does that mean. So the intervals so this is the sign chart for f prime. It's for my derivative. All right, if I'm looking for intervals of decrease, my intervals of decrease would be from negative infinity to negative 1, right? Negative infinity to negative 1, and from 5 to infinity. In other words, the position function from this derivative would be decreasing on these intervals. It would be going down. Okay? Increase. So my intervals of increase would be just from negative 1 to 5, right? I think that's pretty straightforward, increase, decrease. We just read it off the chart. What sometimes gets a little bit more challenging is how do we tell if it's a local max or local min? Now let's think about this for a second. If my function is decreasing until it gets to negative 1, now kind of follow with me. It's decreasing until it gets to negative 1, and then it starts to increase. What is going to happen at negative 1? That's going to be a relative minimum, right? It's going to be a relative minimum value because I'm decreasing and then I'm increasing. So I would have a relative minimum at negative 1. And we would have to find the y value. Of course we can't because we don't know what the function is because I made it up. All right. So now let's look over here. What about if I'm increasing to 5 and then I start decreasing? I'm increasing to 5 and then I start decreasing. What is happening at 5? A relative maximum. So I have a relative maximum here. And sometimes, I'm just showing you, sometimes what students like to do is I like to draw like, decrease, increase, so that kind of gives them a picture that it's a minimum, and they do increase, decrease to give a picture of maximum. Do you have to do that? No. I just like to point out some strategies that other students use that you may want to consider. All right, so we have a minimum value at negative 1 and a maximum value at 5. Okay, so that's what our lesson is going to involve today, is using the derivative to determine behavior of the position. Okay, are we okay? Let's do some examples. Okay, so let's take a look at number 1. The first example is we're wanting to find the tangent line at x equals 1. Okay, so the tangent line at x equals 1. We get to use, it is my favorite equation of the line. Yes, I have favorite formulas. I know that's weird. My favorite equation of the line. It's point slope. So y minus y1 equals m times x minus x1. That is my favorite equation of the line. So what we need to write the tangent line is 3 numbers. We need 3 numbers to write the tangent line. Right? We need 3 numbers. We are going to be given typically this x1. That's this number right here. Right, so now we only need to find 2. Okay, we have 1, we need 2 more. How do you suppose I would find y1? Just plug it in, right? That's pretty straightforward. In fact, that's probably the easiest number to find. Let's just go ahead and find it. So let's do f of 1. We plug in a 1. We get 3 times 1 to the 4th minus 7 times 1 squared minus 1 minus 1. Let's see, what does that give us? So it gives us a negative 6. Check my arithmetic. Okay, negative 6. All right, so great. So we have this one and we have this one. We have one more. We need the slope. So this point, x1, y1, is the point of tangency. Okay, that's a vocab word. Do we know what that means? The point of tangency. That is the point where this line touches the function. Right? It's the point of tangency. So my point of tangency is at 1, negative 6. Now my last task is to find my slope. And where we just have been talking for several minutes about slope. Where do we find the slope of the tangent line? From the derivative, right? From the derivative. So I need to find the derivative. Okay, so we're going to find the derivative, f prime of x. Okay, we're going to use a power rule. Right? Using the definition of the derivative would take like 5 times longer than the power rule. Okay, I'm just saying, it'll take a really long time. It's fun and everything, but we're going to use the power rule. All right, so let's do that. So remember the power rule, we bring the 4 down, multiply by the 3, get 12. So 12x, and I subtract 1 from 4 and get 3. Is everybody okay with the derivative of 3x to the 4th? Okay? Now let's keep moving. We're going to do the derivative of 7x squared. So I'm going to bring the 2 down and multiply it by the 7. So that gives me 14x, and then 2 minus 1 is 1. So the derivative of 7x squared is 14x. We okay with that? Okay? The next one, negative x. So we know that exponent is 1. Okay, so I bring the 1 down, and then I have x, and I have 1 minus 1. What is 1 minus 1? 0. What is x to the 0? 1. So the derivative of negative x is negative 1. Okay? What do you think the derivative of 5x is? I take the 1, bring it down. 1 times 5 is 5. 1 minus 1 is 0. X to 0 is 1. What's the derivative of 5x? 5. What's the derivative of negative 3x? Negative 3. Do we see the pattern? Okay. Those are the derivatives. Now, what is the derivative of this constant, negative 1? It's 0. That derivative is 0. So here's our derivative. We want to find the actual derivative value at 1, because that's my slope, right? We were just talking about that. The slope of the tangent line at the point of tangency. That's what I'm finding. I'm going to put a 1 in here. So f prime of 1. So 12 times 1 cubed minus 14 times 1 minus 1. What does that give us? A negative 3? Yeah, negative 3. Okay, now I have all 3 parts of what I need to be able to write the tangent line. I have all 3. So let's just fill in the numbers. So I have y minus a minus 6. So that would be y plus 6 equals my m, or my slope, is negative 3 times x minus 1. Now, resist the temptation to distribute and combine like terms. Just leave it in that form. If you distribute and combine like terms, you're just setting yourself up for the possibility of making a multiplication or arithmetic mistake. And it's perfectly acceptable in point slope form, which is really one of the reasons I love point slope form. It's so fantastic. Just leave it alone. Put the numbers in, leave it alone. You're good to go. All right? We okay with that? Our very first tangent line that we found. Isn't that exciting? Very first one. Wow. Okay. Let's look at number 2. On number 2, we want to find the function. Now this is a thinking problem. This is a thinking problem. This is the derivative of a function. What function would this be the derivative of? Can we think about that? What function would create this derivative? X to the 5th. Okay, let's check that out. If I take the derivative of x to the 5th, don't I get 5x to the 4th? What about x to the 5th plus 30? Could that be the function? Yes. What about x to the 5th minus 1,000,000? Could that be the function? Yes. So there are an infinite number of functions that have that derivative. That's just an important concept to think about. There are an infinite number because of all the different constants I could use. This is just one option. F of x would be that. That's one, you could have a completely different option than I do, but what would have to be the same in every derivative? The x to the fifth would have to be the same in every derivative. Okay? All right, so let's move to number 3. We're going to do intervals of increase, decrease, and local extrema. So we're going to do what I was talking about on the other slide. So how do we find intervals of decrease and local extrema? What do we need? We need the derivative. So the first thing I need to do is find the derivative. So let's do that. So f prime of x equals. So let's work on x cubed. So the derivative of x cubed would be, bring down the 3x. 3 minus 1 is 2. 3x squared. Okay? Let's work on the next one. We have 3x squared, strangely enough. So let's do the derivative of 3x squared. Bring the 2 down. 2 times 3 is 6. And 2 minus 1 is 1. What about the derivative of negative 4? Is 0. So that's my derivative. Are we okay with that? Ethan, you okay with that? Okay. All right. So now I have my derivative. I'm going to take my derivative and I'm going to set it equal to 0. I'm going to set my derivative equal to 0. So 0 equals 3x squared plus 6x. And then I'm going to solve it. I'm going to get my solution. I'm going to put it on a number line. So let's see. I have 3x times x plus 2 equals 0. Okay, so I can tell what my numbers on my number line should be, right? I need a negative 2 and a 0. Now this is a question that maybe you're thinking in your head, or maybe we're not there yet, that we all need to ask. Where do I check the signs for that sign chart? Now this is going to get extra confusing because in calculus we do multiple sign charts for multiple things. We would have a sign chart for the first derivative, a sign chart for the second derivative, and so forth. So the question is, we have to ask ourselves, where do we go to check the signs? And I'm going to tell you, we go where we got these numbers from. Where did we get these numbers from? The derivative. So we're going to test this sign chart in the derivative. That's where we go. You go where you got the numbers from, okay? And that's as straightforward as I can make it. That's where you go. So I got the numbers from here. I'm going to go check up here. So if I put a negative 3 in, what do I get? A negative times a negative as a positive. If I put a negative 1 in, what do I get? A negative. If I put a 1, I get a positive. So those are my signs. Okay, so now let's do increase, decrease. So increase, my levels of increase are going to, intervals of increase are going to be from negative infinity to negative 2, and from 0 to infinity. Can you put a U there if you want? Sure, you could put a U there between those if you want. I know we've been that's been emblazoned in our memory, everything, right? You've got to put a U there. Yes, you can put a U there if you want to. You can put a comma if you want to. Either one is fine. Decrease, intervals of decrease are basically from negative 2 to 0. And I'm using parentheses because I guess I fall in that mathematics camp that would prefer parentheses. Remember we talked about that. Some mathematicians want to use brackets on increase, decrease. Some want to use parentheses. You could do either. You could fall into either camp. It's fine. Both are acceptable on the AP test. Now let's look at local extrema. So let's look at our sign chart. Okay, so I'm rising till I get to negative 2, and then I'm decreasing. So what kind of extrema do I have at negative 2? We have a relative max. We have a relative max at negative 2, and I'm going to leave that open. Okay, we definitely need this y value. And I'm going to go back to how we find the y value, but that is important. So let's move to this one, to 0. I am decreasing, and then I'm increasing. What's happening at 0? We have a relative minimum. We have a relative minimum at 0. Now here is where so we're talking, all of this is about the position function. All of it's about the position function. Relative maxes and mins are really talking about the y value. That's the important part, right? How high does it go? How low does it go? Many students want to just give the x value. All the x value tells us is where it is. It's like, okay, great, it's over there. That's all x tells us. It doesn't tell us what the relative max or min is. It just says, oh, yeah, it's over there. Okay, that's not enough information for us. We need the y values. Really, really important. Need the y values. So where am I going to get the y values for the relative extrema? The original function. I have to go back to the position function because, you know, the derivative is just describing all about this. It's like, poor little derivative. It's not about the derivative at all. It's probably sad about that, right? Gosh, not about me. It's always about the position. Always about the position. But, you know, that it is all about the position. So if I want to get my relative extrema, I have to go back up here. And I've got to plug in a -2 in here. And I get, what do I get, a 0. I plug in a 0 here and I get a -4. And there's my increase, decrease, and relative max and min. How are we on that? Okay, last problem. We also have to be able to look at a graph and determine which one of those graphs is the position and which one is the derivative. Now, we may be thinking, and some of you probably are, oh, well, that's just a parabola and a line. I know which one is which. Okay, I want to caution you because it is certainly possible to zoom in such a way in a graph to make it look like that's just a parabola and that's just a line. But in fact, it could be, that could be a parabola and that could be a piece of x cubed. We don't know. We cannot assume that. So I'm going to tell you what we have to do. We need to check two things. We need to check extrema and we need to check increase, decrease. These are the two things we're going to check. The first thing I like to check is extrema. That's what I like to do first. I like to look on here and see, is there a relative max or min? Do we have a relative max or min here? We do, right? The black one has a relative minimum. So I'm going to draw, I have a tangent line there. What's the slope of that tangent line? 0. So what does that mean the y value of the derivative must be? 0. The slope of the tangent is the y value of the derivative at that point. They are equivalent. The slope of this tangent line is 0, therefore the y value of the derivative needs to be 0. Well, looky here. What's the y value of the derivative there? 0. That's an indication that we are correct. That this would be the function and this would be the derivative, f prime. Okay, let's make sure. Okay, that looks that way, and I'm sure we're right. But let's also talk about increase, decrease. So we're saying that this black one is the position. So this is decreasing, right? If the position function is decreasing, what should the value of the derivative be at that interval? Negative. Is the derivative's y value negative over here? Yes, that checks. Decrease, negative. This function is increasing on this side. What should the y value of the derivative be on this side? Positive. See how the y value of the derivative is positive? So check, check. That's perfect. So this the blue one is f prime and the black one is f. Okay? So we will be able to, we'll need to kind of pull that apart. Are we okay with that? Questions?